All right, today we are going to dive into Newton's Universal Law of Gravitation. So that's our first objective. Can we state Newton's Law of Universal Gravitation? And then an important part of that is a mathematical relationship known as the inverse square law. So we're going to look at why is that so important for Newton's Law of Gravitation, and it turns out we'll see that again in a number of applications in physics, especially around different types of fields. So gravitational fields, electric fields, magnetic fields. And then of course, we'll get some practice applying Newton's law of universal gravitation. There's an equation and some math involved. All right, so first off, we know sometimes hear the expression Newton invented gravity. Well, no, he didn't invent gravity. I'm not sure you could even say he discovered gravity, but he did have a key insight into what determines the gravitational pull or gravitational force or acceleration that we experience on Earth. And you may have heard the story that he was sitting under a tree and the apple fell and hit him in the head, and that's how it came to him. Well, nice little story, but the real story is that he made a connection between an apple falling to the surface of the Earth, so a short distance, and the moon also falling towards the Earth. Okay, now, what do we mean by the moon falling towards the Earth, right? We know the moon moves in a circular orbit or very close to a circular orbit around the Earth, okay? And if you remember from our discussion of circular motion, there has to be a centripetal force and centripetal acceleration that's causing it to change its direction, always turning inward towards the Earth to stay on that circular path. So you could describe it as falling back towards the Earth. That's what allows it to stay in that circular orbit. Okay. Now, it turns out he was able to determine, based on the time it takes for the moon, right, to go around the Earth, about 28-day cycle, that it travels about 10.4 meters in 1 second. That would be its tangential velocity, okay? And that the moon was about 60 radii distance from the center of the Earth. So one radius would be one radius of the Earth, okay? So it's, you take the Earth's radius and about 60 times larger, that's how far the moon is from the Earth, okay? He also noticed that when an apple falls to Earth in 1 second, it falls about 4.9 meters in 1 second. So in order for the moon to stay on that path, it would have to fall about 1.36 millimeters each second, okay? Not very far, but you gotta remember it's a really big circle, right, that the moon is traveling on. So he began to look at that ratio, the moon, and the apple falling and the Earth falling. So they both fell these distances in 1 second, 4.9 meters and 0.00136 meters, right? If we take that millimeter and convert it to meters. So what's so special about that ratio? Well, turns out that ratio is 3,600. And what's so special about that number? It turns out that is the distance of the moon from the Earth, 60 radius. It's 60 times further away from the center of the Earth than the apple is. And if we square that 60, we get 3,600. So what Newton began to think about is whatever force causes that apple to fall to the Earth has to be the same force that causes the moon to fall to the Earth. The only difference is their distance from the center of the Earth. And that ratio of 60 times is what gave us that overall ratio of 3,600. So he concluded that the apple falls farther than the moon by a factor of the ratio of the radius squared. So what? Well, that's what led him to this universal law of gravitation. And here's what he came up with. The attraction to the Earth of the moon and the apple are due to the same force, and the attractive force varies inversely with the radius squared, okay? Or what we'll see in a minute is the distance squared between the two objects, either the moon and the Earth or the apple and the Earth. So here's what his law says. Every object attracts every other object with a force that is directly proportional to the mass of each object, okay? So the larger the mass, the greater the gravitational force, and it's directly proportional. But the force is also inversely proportional to the square of the distance between the center of the mass of the two objects. Okay, we're always measuring that distance between the center of the two masses. So mathematically, here's how we would show that, right? If it's directly proportional, it's going to be the mass of one object times the mass of the other equals the force, or is proportional to the force. And inversely proportional, notice the distance squared is down in the denominator. That gives us the inverse variation. So the greater the mass, the greater the force. The greater the distance, the less the force, right? So as you get farther away, the gravitational force becomes less. Now, he wanted to actually calculate it, right? And see if the numbers agree. And they do if you include something called the universal constant, okay, this big G. So this universal gravitational constant is a kind of fudge factor here that allows us to get the accurate forces. So basically this number comes from the force that you would get if you had two masses, each with 1 kilogram of mass, separated by 1 meter, right? Which means all the values for M and D are 1, and then that simply leaves you with G. So G is a very small number, 6.67 times 10 to the negative 11. Now, the units are kind of strange. We don't need to worry about those too much. It just makes sure that our overall number comes out to be units of newtons for force. But the key is that gravitational force, 6.67 times 10 to the negative 11th. So you could say that number is a unique property of the universe that we live in, right? And that number applies to gravitational force calculations, whether they're on Earth or on the sun or anywhere, as far as we know, in our universe. All right. So we mentioned earlier this concept of the inverse square law. The gravitational field strength varies by the inverse square law. And that is talking about the distance squared, right, down in the denominator. So let's just look at an example here. Think of the gravitational force as a field force, right, emanating out from the center of an object like the Earth, okay? And if we came out one diameter or one distance and had a force of F, what happens if we double that distance, right? So notice as we double the distance, the gravitational field has to spread out over a larger area. Think of us moving out on a surface of a sphere. And how much does it increase by? Well, it's got to spread that gravitational field over 4 times the area. So we wind up with a force at any point on that surface that is 1/4. And that makes sense because if we double the distance, but it's squared, that gives us a factor of 4, but that 4 is in the denominator. So we actually get 1/4 of the field force. What if we tripled the distance, right? What is that going to do to the force? Well, what is 3 squared, right? 9. So we're going to have 1/9 the strength of the gravitational field or force if we were to triple the distance, right? And so on, right? If we have 4 times the distance, we would have 1/16 times the force, okay? So what you're seeing is that as the distance grows, the gravitational field becomes smaller very quickly, right? If we were to be 10 times the distance, the force would only be 1/100th, right, of what the original was at a single distance. So this is what we mean by this inverse square law, and it shows up a lot of places in physics. All right, so let's get a little practice here if we can apply these concepts. We're going to start with two masses a distance d apart, and they produce a force of F. Now we're going to make some changes, and I want you to see if you can figure out how it would change the force. Okay, so let's look at A, right? We're doubling one of the masses. So what is that going to do? Well, that factor of 2, right, is going to be up in the numerator because it's mass 1 times mass 2. So if we're going to double the numerator, that's going to overall double the force. Okay. How about B? We doubled one force and tripled the other force. So the factor of 2 times another factor of 3 in the denominator means that we're going to increase the force by a factor of 6. Let's do C. The masses are the same, but we've doubled the distance. So this takes us right back to this inverse square law, right? So if we double the distance, that means that we're going to have a reduction in the strength of the force by a factor of 1/4, right? Because the 2 has to be squared. So F over 4. Now, how about if we cut the distance in half? We know the force has to become greater. So this one's a little bit trickier, right? Because we've got a fraction in the denominator. So 1/2 squared is 1/4, but if we're dividing by a fourth, that's the same as multiplying by 4, right? And then the last one here, we got both the mass and the distance changing. So we've tripled the mass, that means triple the force, but we've doubled the distance. And we know from up in C, right, that's going to give us 1/4. So we're going to multiply by 3 and divide by 4. So we would have 3/4 or 0.75 of the original force. Okay, but this is the key concept, right? How does mass affect the gravitational force? Directly proportional. How does distance affect it? It's the inverse square law. All right, let's put some real numbers in here. So why do they call it universal law of gravitation? Because gravitational force exists between any two objects that have mass. It doesn't just have to be between huge planets like Earth or the sun or Jupiter or anything else, okay, or our moon. Any object that has mass. So Arnold and the Terminator, they both have mass. So we could calculate the gravitational force between the two, but we need to know some information. We need to know their masses, okay? So here's their mass in kilograms, and we need to know the distance. Let's say they're 15 meters apart. So we can plug that into our formula, right? G is our universal constant. We have the two masses and we have the distance. Just don't forget to square the distance. So here's what that looks like if we plug all that in. Now, you're going to use your calculator a lot on this unit, and you're going to be working with some really big numbers and really small numbers in scientific notation. So I would recommend you figure out how to use scientific notation on your calculator. It's very important that you're able to do that. That's the easiest way to enter in these big numbers or small numbers in case of G, right? 6.6 times 10 to the negative 11. All right, if we plug all that into our calculator, turns out we get a gravitational force of 3 times 10 to the negative 9. So that would be, right, 0.0 with 8 zeros and then a 3. So very, very small force. So do you think Arnold or the Terminator feel this gravitational attraction between them? Does Arnold feel like he's being pulled towards the Terminator or the Terminator being pulled towards him? No, it's such a small force that we don't feel it. So if you're sitting next to somebody at a table, right, there is gravitational attraction between the two of you, but it's so small you don't feel it. You never see two people just being pulled together, right, by the gravitational force between them, but yet it does exist. We can calculate it. All right, so we use this formula to find the gravitational force. But remember, the value of G that we've been using all year long is actually the acceleration due to gravity. So how could we use this formula to find the acceleration due to gravity? Well, let's go to Newton's second law, right? The acceleration is equal to the force divided by the mass. So if we take our formula, let's say we want to find the acceleration experienced by the mass 2, whatever that second object is, then we want to divide, right, Newton's law of universal gravitation by the mass 2. So let's do that. And notice, right, we're going to cancel out that second mass, and we're just left with the universal constant times the mass divided by the distance squared. So it's really important to note here that this would be the acceleration that's generated by mass 1. So if you wanted to say what is the acceleration due to gravity on planet Earth, you would use the mass of planet Earth. Even though you might be saying, what am I going to feel as a human being standing on the surface of the Earth? What am I going to feel in terms of that acceleration? So in this formula, the mass is always that of the object that is generating the gravitational acceleration. Okay. Now, you could use my mass, right? And that would be the acceleration that the Earth feels being pulled towards me. It's a mutual force, but that would be so small, right, that we don't really think of the Earth being attracted up towards to us. It's always us being attracted down towards Earth, because that is the much stronger force. That's the much greater acceleration. All right, let's look at another application here, and then we'll wrap this up. So we want to use Newton's law of gravitation to determine the acceleration of a 75K person at two places. One on the surface of the Earth, okay, so that's kind of the normal gravitational acceleration. We would expect it to be pretty close to 9.8 or 10 meters per second squared. But we also want to calculate what is the acceleration due to gravity up on the space station. Because when you're up in space, there's zero gravity, right? Well, let's see what Newton's law says. Okay, so we're going to calculate the acceleration for both of these cases. So what else do we need to know? We need to know the mass of the Earth, right? And you're given up above the distance from the center of the Earth to the surface, or the center of the Earth to the space station up in orbit. All right, let's plug it in. So surface of the Earth, we're going to use this formula for acceleration. We only need the mass of the Earth. So we plug all that in, we get 9.79 meters per second squared. So remember, the more precise number we use for acceleration due to gravity is 9.8. Well, you can see that's exactly it, right? 9.8 or 9.79 meters per second squared on the surface of the Earth. Okay, so no surprise there. It's what we would expect. But how about on the space station? Same thing, but now we have a greater distance. The mass of the Earth is still the same, but it's just going to be a greater distance. So when we plug that in, notice we get a little less than kind of the normal acceleration due to gravity, right? 8.82, but it's not anywhere close to zero. I thought when you're up in outer space, there is zero gravity. What's going on here? Well, was Newton wrong, or does this formula still work? The formula still works, right? But that's the big question. If acceleration due to gravity on the space station is just a little less than that on Earth, why do astronauts experience weightlessness? Or why does it appear that they are weightless up in space? Well, think about it. What is that space station doing? It is traveling in a circular orbit around Earth, and it's basically falling back to Earth at a rate that keeps it on that circular path, just like the moon, right, was falling back towards the Earth. So if you're inside the space station that's falling back to Earth, and you're falling at the same rate, what is that going to feel like? It's going to feel like you are weightless, right? Just like an elevator, when it first begins to drop and move down, what does it feel like to you? You feel a little bit lighter, right? You feel weightless for just an instant when that elevator is accelerating downward. So that's why both the astronaut and the space station are falling at the same rate back towards Earth in order to stay on that circular orbit. And that's where the sensation of weightlessness comes from. Now, if you were not traveling in a circular orbit, but just stationary above the Earth would pull you back towards the surface. You would accelerate at 8.82 meters per second squared and come blasting back into Earth, right? I mean, that would be pretty nasty experience because you're going to enter the atmosphere and basically burn up, right, before you could pull a parachute and land back on Earth. All right, that's it. So we are able to state Newton's law of universal gravitation. We understand how the inverse square law is a very important part of that, right? The greater the distance, the gravitational force falls off very quickly. And we've had some practice applying this and doing some calculations to calculate the actual gravitational force or acceleration. Okay, that's it.